Hello, everyone. Welcome to the second class. I see some of you have already turned in your assignment for the naive base from the first class. The rest of you keep trying and try to find some more time. And let's see, if you have any questions or get stuck, that's another conclusion as well. You can always get back to me and say, hey, this is the reason I got stuck at this point. How do we go ahead from there? Okay, so let me share my screen so that we can have our slides ready for the second class. All right, so what I'll do is show you again the syllabus. This is something I like to do every time before I start the class, just to give you a feel for where we are and where we are heading for. So this was our first class. We covered, generic introductions to different paradigms in machine learning. We obviously did a lot of basics of probability and statistics. We covered one technique for classification. It's called the naive Bayes. And then I said we are going to move the regression aspect, which is this part, to the next class, which is what we're doing. We're going to cover that now. And then there was another task that we tried to identify, put forth, which was if you could identify data sets from some of these online links that you could possibly use for your projects, that would be great. You can email me on this to start with. So everyone just send me an email saying, hey, these are the 3 data sets, these are the links that I've identified for either a regression or a classification project. And then we can go over that sometime in the video call later, but most of that could be done in the email, the back and forth on that. So as you see, today we're going to start with, so like we did a very naive classification method last week, this week we're going to start with some of the simplest regression methods that you could do. And one of the simplest, or the starting point there would be the linear regression model. So we start with there, and then we keep going as time permits. To me, it seems like there would be some change on, we're going to finish that. We're going to start with generalized linear models, but we would need to be having a lot better, insight on how this model works. So just a few slides may not work. So in the interest of not cramming up things just for the sake of it, I'll be moving some part of this to next week as well. So we'll have like a bit covered now, more like an introductory, and then we'll have like a part 2 in this next week. That we will have a better focus and more time for discussion and stuff. Let me get started with the slides. Okay, so yeah, linear regression. This is some of the most introductory models, but yet very useful in practice in general, even today. On the regression side of things, just like naive Bayes was for classification, like I just said. So what is a linear regression model? So I want to start with some sort of an example. If you had a set of input variables, which we do have in machine learning or in statistical modeling, so let's call those input variables x1, x2, and so on. And then you say you had an output variable which you want to predict. And if your output variable is a real valued variable, so that's when it's a regression model. If it's a categorical variable where it only takes a few categories or classes and cannot be compared on a number line, then it's a classification model, right? You cannot put spam and no spam on the number line. There's no real numbers to it. These are just categories or buckets or classes. But this part stays the same. You have x1 and x2 or input variables. The part that stays the same, I was trying to mean was your input variables could either be numeric or could be categorical, or it could be a mix of both. But your output, if it is numeric, then it is a regression model. If your output is categorical, it is a classification model. So this is a simple example. Let's see. So salary of a person is usually based on years of experience and levels of education, and obviously based on other things. But assuming only we are considering these 2 variables of experience and education as our x1 and x2, if you want to try to build a model that can predict the salary of a person using some input training data, and then you test it on your test data. And if your restriction is that your model needs to be linear. So what do you mean by linear? So this is literally a linear plane, a linear equation, right? If you had y equal to mx plus c, that is the equation of a straight line. So linear is referring to the straight part. And so if you have multiple variables, more than x, so if you have 2 variables or 2 or more, or maybe 100 variables, then it's going to be, instead of a linear line, it's going to be a plane. It's going to be a straight surface in a higher dimension. So you're restricting yourself, your predictive modeling, to a class of functions that belongs to the class of linear functions, basically. So you can fit any linear function. So what is it that needs to be figured out in terms of the model fitting? You need to figure out what the intercept is. This is the M, or sorry, this is the C in the MX plus C kind of a terminology. So this is your intercept to the y-axis, so where it's meeting y. Then your other coefficients, the beta 1s and beta 2s and so on and so forth, depending on how many variables you have, is what you want to figure out. And your goal is to minimize the error. So whatever you're not able to predict using y minus all of this, whatever is left out, is the error. So a better way to quantify the error is, as we go forward, we'll see. Instead of just doing a difference, you want to do a squares. But let's not jump ahead of ourselves. So a few of you might have already seen linear regression or heard of it a lot of times before, because it is a very basic model. It shows up a lot of in a lot of places. So for those of you, maybe you want to stay a little patient if you know this stuff already. So as we get going into more techniques and classes and the science of things and theory and stuff in the future weeks, it'll start challenging you even more and more. If you've already seen these models, you'll be learning newer things. But there's a good starting point for regression. So yeah, so like I said, it's a straight surface that you're fitting. So it's just a quick plot for a specific set of coefficients, 50, 10, and 7. Well, 10 and 7 are the coefficients, 50 is the intercept. As you see, it's meeting the y at 50. Somewhere the 50 is in here. Also, like anything in math, you can always have a very simple explanation, but you can always dig deeper. So there's a lot of theory you can do even for a simple model like linear regression, and a lot of assumptions you can take from the statistical side or just the math point of view. We will get to that gradually today as well. So one of the things, although I was bringing this up because if you see here, I don't call it y anymore. I'm calling it expected value of y. So what is it? Why are we using an expected value, right? So just to recollect from our basics we did last week, expected value is the integral of the number that your random variable can take times the probability of that number being observed, right? So it's a weighted notion of average. So usually in an average, you're just summing up everything and dividing by n. But in an expectation, you're weighting your sum unequally based on the probability of it being able to occur, right? Because the probability is the number of times something is being observed by the total number of possibilities. So that's a fraction. And it's not the same as 1 by n, which is the case you're using in a usual average, where you just sum things up and divide by n. That is, to be precise, an estimate or like a statistic that is trying to estimate the population average. But if you had a random variable with a distribution function, right, the population notion of the expected value or the mean or the average is done by the expected value. That's the expected value. You also have a notion of variance and other things you could calculate. So why are we calling this expected value of y? So if I did that, I need to assume that there's some random variable in here or some random function or some random behavior going on in here, right? Only then you have a random variable in y, and only then you can have an expected value. The assumption, the statistical assumption, is coming basically from the error. The error that you're not able to model, the assumption in linear regression from a statistical standpoint, is you assume that the error is distributed, is coming from a normal distribution of some mean and some variance, which you don't know. So if you take an assumption that you want to minimize an error coming from a normal distribution, so that kind of noise, then since this is a normal random variable, this is a random function, because a function of random variable is also a random function. So the left-hand side is also a random variable, and that's how you have an expected value of y. So basically, it's telling that y has a distribution of itself, of its own. So if you have a distribution, then the point is, which point in the distribution do you consider as your as the predicted value? Because it's not one number anymore once you put a statistical assumption of a distribution here. So if you want to pick one number, a good idea is to pick an average. You don't want to pick a number that is not very likely to occur in terms of its distribution function. So there may be some probabilities at which y is more observed. So what would be a good guess you would take if you were to pick a number? An expected value would be a great guess or a good starting point. So you're trying to model it. So this is just the mathematical standpoint of an equation. Here it's just math. But once I put in that distributional assumption in here, it becomes a statistical model. And that's another way of looking at linear regression. That's why the expected value of y comes in here. We're going to study this a little more in detail as we go through. So yeah, this is just saying if you had more than one x, then it's no longer a straight line, it's a straight surface, right? It's a hyperplane is what it's called. It's a straight plane in a high dimensional surface. So if you have many variables, then you have a hyperplane in high dimension. Okay, now, yeah, this is some different plots. This is not linear regression. Unless this was supposed to be looking linear, which it's not looking at, unless we've done some. No, this is definitely not linear regression. There's a big curvature. This is called extrinsic curvature. So this is a linear regression curve. So if you see here, this is having the curvature because if you see the equation in here, it has. Let me take this out. Okay, you see my screen?
Yes, we see your screen.
Yep.
Yeah. There was this little comment. I wanted to remove that because I wanted to show this. Okay, so yeah. So if you see this here, you have this quadratic. The degree of this equation is no longer linear. It's no longer 1. It's 2. So there's quadratic terms, x1 squared, x2 squared. That's why you're seeing this curvature coming in here. So this is not linear regression. This is linear regression. So here, this is all linear in here. Well, this might have a little bit of curvature that we're not looking at because there is well, this is still linear regression, yeah. The degree here is x1 times x2 is going to be 2, but this is considering it as a linear line. This may not be a great example. I need to check if there's any curvature. But there is, there is, when we get to generalized linear models, the point I'm trying to make with this is, although the degree is 2, is this. The fact that you're only doing a linear combination of terms, which is a linear combination means a sum of products, basically. That's a terminology used for sum of products, which is what you're seeing. There's a sum, and then there are products at some point. Here, the product is just with 1 because it's the intercept. So the way the coefficients in these terms are interacting is kind of linear right now. So that's the linear part. Because the generalized linear models, which we would cover towards the end of this lecture, would also have this linear combination, which is why it's called a linear model, but it's not a nonlinear model. You can put a nonlinear function before this, and then it becomes a generalized linear model. We will get there. Let's not jump ahead of ourselves. Let's see. Okay, so the goal is now to estimate the parameters, right? The betas, like what these numbers are supposed to be given the data. So the way to do that is known as the method of least squares. It's very popular. It's kind of very intuitive as well to understand. So this is our setting. We have data set for output variable. We have a lot of input variables. So let's keep going. So yeah, so what you want to minimize is basically your error, right? Your error, your epsilon. So you want to minimize y minus this term, the rest of the term, which is the linear regression model. This is the model. This is y minus. So this is what is left out. Now, you don't want to just leave it that way. You want to square it because you can have errors on both sides, right? You can make positive or negative errors. So you want to either have the absolute value or like a squared objective function so that an error on either side is treated as an error and errors don't cancel out. Do you see what I'm trying to say here? Let me show you. So if you see this, if you had some data, if this was a 2D problem, if you had some data, and if you fit a line that went like that, this is supposed to be a straight line, although it's a cartoon. So these points were explained well, but these 3 points of x1, x2 were not explained well by the y curve, which is the line. So this is your error, right? So there's some amount of error here. There's some error here, from here to the line, straight line. From here to this is the distance from your point that line could not explain to whatever it did not explain. So here the errors are very small, almost 0, the 3 points that it passed through. So now this is a positive error, this is a negative error because there's 2 directions going on. You don't want to make sure that a positive error and a negative error cancels out, and your error, it shows that your error function is much lower than what it is, because that's not what you want to measure. You want to measure any deviation on both sides. So a square would be a great way to do that. So that's the reason you don't just do the difference, you do the square. So that's the method of least square. So you want to reduce the sum of these squares. So what are you summing against? If you have n rows in your data, n samples in your data with 2 variables and 1 response, you want to make sure you measure the error against each point, just like I was drawing in that little cartoon. So you want to sum up all of your errors. So you want to minimize that term, because you want to find coefficients, betas, that minimize this error, because then you have a line that defines your data as well, that goes to your data as well as possible. Now, how do you do that? So that's when some calculus kicks in. This is basically a convex function, because it's a quadratic. The degree of your objective is quadratic. This is not a linear function anymore. Your error function, your loss function is quadratic. So degree 2, because that's the highest degree you can get when you expand this. And it's a quadratic function. So quadratic function always has one global minima. So this, in the 2D case, there's only one minima. You don't have things like this happening. This happens when you raise your degree from 2 to 3, 4, 5. As you keep going for higher order polynomials, you would have complicated functions where you have this minima, there's another global minima. So this is a little more harder to optimize. So this is called non-convex, this is convex. Another definition of convexity is if I take any 2 points on the curve that I'm trying to check the convexity for, if I join those two, it will always stay within this curve. But if I take, in a non-convex case, if I take 2 points, you would see intersections happening. This would not happen here. You would never have an intersection. Whatever point you join, in a convex case, there is no intersection. Then there's many other mathematical definitions you can take based on the derivatives and stuff. So anyway, the thing is, if you look at this curve, if you compute the gradient or the derivative at any given point, you will see that at the minima, the global minima, your derivative, your tangent looks like this. The derivative of this curve at this point at the minima looks like parallel to this line. So which means the derivative is equal to 0, because the derivative is measuring the angle you're making with respect to the axis, right? So here your derivative is more. This is the angle you're having with respect to the axis. So a good way to find, if you have a convex function, you want to find its global minima, all you need to do is compute the derivative of that function and set it equal to 0, because you want to find where the derivative is 0, and if you solve that equation, you'll get this point automatically. Which you cannot use this approach in here. You would obviously use derivatives, but just setting it to 0 will not give you the global minima if it's non-convex. Okay, so that's exactly what is being done in the least squares estimation of parameters beta. In the linear regression, you're going to find the derivative and then set it to 0. If you see the derivative of this with respect to beta, you want to set the derivative with respect to beta, right? Because you said that's what you want to find out. So you'll see, so the derivative of this is 2 times this, right? And into x power n minus 1. So you have that term. Also, what you will see is you need to compute the derivative of a function that is inside the square, right? Because this is if you see, it's a composition of 2 functions, the square function, and then there's an internal function. So first you do the derivative of the square, that brings the 2 on the side, and then you want to find the derivative internally. So that's what I want to put in here. This is just a placeholder. This is saying this times the derivative of whatever is inside the bracket. So upon expanding that, you would get the follows, because there is, so if you see, the intercept is something you don't have to care about. You care about internal stuff, the internal coefficients, the most. So if you take the derivative there, you have this xij term, so that comes in onto the side as well. So basically, if you expand that, all you will see is a summation. So you will have n times yi times n times beta naught, that's n times of this. As you keep doing that, it will look like this. Here, I'm just opening this bracket up, this summation of individual terms written down individually. And then the yi, I passed it onto the other side. So sigma of yi equal to sigma of this plus sigma of this, which is what's going on here. and beta naught gets summed up n times, so it's n beta naught, is this. So basically, this is a lot of algebra, but there's a bigger point here, which is the important part. This thing, anyone can work it out on their paper. The bigger point is you have a convex function you want to minimize with respect to a parameter, so you set the derivative of that with respect to be 0, and then solve for that parameter. For reasons as I showed in the cartoon. So that's what's going on. This is all just opening things up. So another way to write this is you can multiply it by any given xi term. So then that gets multiplied on all sides as well. So here, this what's happened from this equation to this equation. But all this is just algebra. This is one way of writing it, or you can just solve for this. Either way, it works out. So you want to solve for these equations with respect to beta. So so you can set the derivative with respect to beta 1. You get some equation with respect to beta 2. You get another. You solve all these equations, and then you, by setting the derivative to 0, you get the solution. This is an example again of some data set. I mean, by now you would have an idea of what this stuff is because of what we discussed last class. You have a set of variables, x's, you have a set of y's. You want to use x's to predict y, right? So here the example is pull strength of a wire bond in a semiconductor manufacturing process. So you have a wire length and some d height. So there's something to do with the physical aspects of the process, but the goal is to be able to predict this pull strength variable. So if you look at the relationship, because linear regression, yeah, go ahead. Yes. Hello? Yeah, I saw somebody was trying to ask a question or some. Okay, so let's keep going. Okay. So if you see, oops, I should have done the current slide. If you do some visual exploration of just your variables before even fitting the model, if you plot strength versus length and strength versus height, length versus height. So this plot is, say, strength versus length, because you have 3 variables, right? This length, height, strength, everything. So strength is your output, length and height are your input. So if you see there is a linear relationship between strength and length, reasonably linear relationship, looks kind of linear. But strength versus height, this cannot be explained by a linear model. If you're only trying to predict strength by height, it's going to have a lot of error because you pass anywhere a line, there's going to be a lot of points going out. So this is just a visual exploration of data to see if the linear regression is a reasonable model for your any given data set. So you can look at the correlation. This is known as the correlation coefficient. So that measures the linear dependency. So you can also compute correlation if you didn't want to do this plot. So if your correlation coefficient is 1, it means it's linearly dependent and increasing relationship. If it was -1, it would have been like this. But still, it tells you that there's a linear relationship between any 2 variables. But if its correlation is close to 0, there's kind of no way you can get a straight line explaining the relationship between the 2 variables. Okay, so same thing, you put in x1, x2 in here, you solve for your betas using those equations, you get the answer for your betas should be. These are the normal equations. You solve these equations. You have 3 unknowns, you have 3 equations, so you get something. Now, this is what is usually implemented in your computers, and this is how I usually do linear regression. So these equations are generalization. You don't want to write these stuff every time if you have like 100 variables. There's a better way to deal with that by using some matrix notation. So this equation, which is your linear regression equation, this whole thing, can be written using matrix notation as follows. Your y is a vector now. It's not an individual point. Your x beta plus epsilon. Epsilon is a vector of errors. Your beta is a coefficient vector because you have a vector of coefficients. Now x is your input data matrix. This is your matrix of data basically. Anything other than the y variable, right? You have a lot of rows of data with different variables, k variables. And you're putting ones before, but you're appending ones, a column of all ones, just because your beta naught, if you see, is always the same, right? Regardless of whether you're predicting this row, this y. So that's why beta naught is always getting hit by 1. So if you remember the matrix multiplication, if you just think through this in your mind, this is beta naught plus beta 1 x11 plus so on till beta k x1k. That will give you the prediction for y1 if you had the right betas estimated, or your prediction will be way off, or if the modeling assumption of linearity is not true, like in the plot that it showed, even then you'll be way off. So that's the reason. Even whatever y you're predicting, your beta is, your intercept is staying the same, right? That's the point of the intercept. So that's why you put in all these ones in here. So before you do this linear combination, you're always adding up just beta naught. So that's why this is a matrix notation of this. Now the great thing is all you need to do is you want to look at y minus x beta, which is your error, then put in a norm on that, which means you're doing sum of squares of that error. So y minus x beta means what? y1 minus this, y2 minus this would be the second term in that vector. So y minus x beta would be another vector. And also remember, this is what? N by k, this is n by k matrix. This is a k by 1 vector. So the product of x beta is again a vector. It's not a matrix. It's going to be n by 1, right? So this is n by 1, this is n by 1, this is n by 1. N rows and 1 column. So all you want to do is y minus x beta will be another n by 1 vector. It would not be a matrix. Y minus x beta is a vector. Then all you want to do is that's a vector of differences, right? But differences is not what you want to sum up. You want to sum up the squares of the differences, the squares of the errors. So you put squares to each term in that vector of y minus x beta and you sum them up. You get the error, which is the epsilon, that epsilon square, which is what you want to minimize.
So,
yes. Yes.
So why we have to get square? So for example, one side is a -2 and another side is a +2. So you want to make sure that both are like a 4 plus 4 totally 8. Is that the reason you want to make a square root?
Yes. Well, yes. Because if I just add it up, it will say my model has 0 error, which is not true, right? As you can see, there is 2 errors you made of -2 and +2.
Oh, you mean, okay. So -2 plus 2 is neutral. Okay, 0. You don't want to do that.
Yes. Or even if you had 3 and -2, the real error is 3 squared plus 4, right? But you don't want to do 3 minus 2, 1 and say the error is very little.
Oh, got it.
So that's why. So that's why you do the sum. Or you could also do the absolute value, which is another technique. It's called lasso. But in linear regression, people literally do square. So your error, y minus x beta. Now I said this is a vector. You want to do the sum of squares of that elements and add it up. So that can be written down in matrix notation as y minus x beta transpose y minus x beta. This is anytime you have x transpose x kind of thing, or like a vector y z transpose z, all it is doing is sum of squares of products. So what is z transpose z? It is z1 square plus z2 square, well, z1 square plus z1 z2. So you're doing all this sum of squares is, so I think it's hard to talk a few things, so let me write it down. So if you had a row vector and a column vector, if you had 3 entries in here and then 3 entries in here, if these both were the same vectors, so if this was z and z times z transpose, and by the way, whenever there's a notation, when I say z and z transpose, people have a question usually, is z the row vector or is z transpose the row vector? The transpose is always the row vector, so this is z transpose, this is z. So what is happening? You're multiplying the first element with the first element. So z1 times z1, which is z1 square, then second times second, right? z2 square plus z3 square. So if you wanted to compute the sum of squares of elements in any vector, which is z1 square plus z2 square plus z3 square, all you can need to do in matrix notation is multiply it with its transpose. So z transpose z will give you the same thing. So that's what's going on here. So you wanted to get the sum of squares of errors, right? So error is y minus x beta vector transpose y minus x beta. Now you want to minimize this. I said this is a convex function because of the degree 2. So what you want to do is you want to take the derivative of this with respect to beta and set it equal to 0. And when you do that, you would get this equation. This is the formula for the least squares estimate of your coefficients. So this is x transpose x inverse x transpose y. So all of this, when you multiply it, because this is n by 1 and everything else is, this is a column vector and these are all matrices. So in the end, your result will be a vector, which is what you need. So that you will get an array of the coefficients, including the intercept in it, in that order, beta naught, beta 1, will end up in this. So all you need to do is, instead of writing all that equations, if you had, naturally your data set is in this table or data frame kind of format, right, in x's and y's. All you need to do is compute this formula. You would get all the coefficients at the same time. You don't need to write these ton of equations and by hand. That's how the matrix notation is helping us here. It's doing the same thing. This is a very popular formula. And if you want me to derive how you got from setting the derivative of this to 0 to this by solving that equation, I can do that as well, if you wish. Okay, so basically, if you, in matrix notation, so I'm just repeating the same thing. This is the difference of the residual, but you want, in the difference of the residual in a vector format would be equal to y minus y hat if these two are arrays by itself. And here you're looking at each individual term, which is the previous approach. So yeah, it's basically repeating the same thing. It's doing the example. You're computing the x transpose x first, then you're inverting it, then you're computing x transpose, you're multiplying everything, then that way you get the answer. So it's a working example. You can do this in computers these days, right? You just save this as x variable, as y variable, and you apply this matrix algebra equation, and you get the answers. So your beta variable in the end becomes like this. So beta naught is 2.26379. Your intercept, these two are your coefficients. Yeah, so there's too many examples. Let's see where we are on time. Okay, good. So from our perspective, this is a typical output that R returns. This is a screenshot of it. These arrows are not going to be there. The blue stuff is something that I added. So there's a lot of information in here other than just the betas, right? So it's kind of good to understand what else is there and what it means and how to interpret the output of the computer, the packages that R returns. So this is the equation. If you see, it returns coefficients. These are your beta naught, beta 1, beta 2. This is what the main coefficients are. It also says constant means intercept. It says this coefficient is with respect to this variable. So it's basically this times length variable plus this times height plus constant gives the equation. Now there's a lot of other things other than that. We're going to cover some of these, and the rest of it will need some other training that I need to give you, right? Because it takes concepts from other parts of our course. So when we get there, I will show this again as well. So, but for now, I will give you some high-level intuition of how to interpret this. So the standard error is basically some sort of a variability it is assuming around this intercept. So it's assuming there's like an error bar. So it's 2.264 plus or minus 1 is what the constant would truly be. The length, it's assuming the error bar is much smaller, and height even more. So there's a better estimate. So it's saying it may not be exactly 2.74, it may be 2.74 plus or minus 0.01. This is 0.01 plus or minus 0.002. That's what the standard error is measuring. This is the results of some hypothesis testing, which we've not covered yet. It's going to be part of our course in future lectures. But a hypothesis test, just to give some intuition, is, we will cover it in detail, but give an intuition is, you basically have a null hypothesis and an alternate hypothesis. So hypothesis is just like an English word, right? So either this is true or that is true. Your hypothesis is like two imaginations, but which one is exactly true is what you want to figure out from a statistical point of view, quantitatively. So here the hypothesis that they're measuring is, they're trying to see if any of these variables are useless, right? Maybe only some variables are more than enough to get a good prediction, because you may have 1,000 variables, maybe only 900 are good enough. So here they're measuring the hypothesis of, can constant be, what does useless mean from a mathematical point of view? If beta naught was 0, it is equivalent to saying the intercept is useless. Or if beta 1 ends up becoming 0, it ends up, if that is good enough, it means length is 0, right? Because you're multiplying with 0, you're not taking length anymore into consideration. So the hypothesis they're measuring is this variable equal to 0 versus this variable equal to 0 versus equal to 0. And then the p-value is a little more complicated concept. It measures, this is the result of the hypothesis. So do I go with the 0 assumption or not equal to 0 assumption? Those are your null and alternate hypothesis. So basically, if your p is very low, it means you can strongly reject the hypothesis that length and height coefficients have to be 0, which means these two are useful variables. So here you're not able to reject it at a point. If it is less than, you can put what is reject? What is low enough? You need a threshold, right? Is 0 the lowest, or anything less than 0.05 is low, or anything less than 0.01 is low? Based on whatever your threshold, you can decide whether the intercept is required or not. But definitely, as you see, the length and height, the null hypothesis of them being 0 are strongly rejected because they're the lowest they can go. So it means those are useful variables. You don't want to drop them. Yeah, so analysis of variance, all of this we're going to cover in future lectures. But for now, we're studying linear regression, so you know what the coefficients are. That's in here. This is the part that's more important for this lecture. When we get to these concepts, then we can, once I tell you what an alpha variance is or hypothesis test is, then we can interpret these numbers more. Okay. So, any questions at this standpoint or some discussion before we switch gears a little bit and jump into generalized linear models?
What is VIF?
VIF. Okay, so it's basically measuring linear dependency. So let me show you. So there's something called heteroscedastic. Let me draw some diagrams. So yeah, linear dependency. So there's a term called multicollinearity. So let me show you. This is a good, yeah. I will use a little more math, but I'll try to keep it simple. So in linear algebra, like in matrix algebra, if I give you two vectors, just look at listen to the concept for now, and then I will apply to the VIF situation. The concept is this: I give you two vectors, x1 and x2, and if I tell you, if I tell you x1 is equal to some number, right? Some scalar number, some alpha times x2. Or if I tell you it's equal to some alpha times x2, this is another alternative. Say plus some scale, well, what do you call this? Some translation, right? You're just moving it aside from there. It's a linear combination. If I tell you that any of your input variables, if you had two variables, and if I tell you these variables are already linearly dependent on themselves, right? So x1, you have y in your regression situation, you have x1, you have x2 if it was two variable based prediction. And if I said x1 was already linearly dependent on x2, because you can write a linear equation saying x1 equal to alpha times x2 plus b, right? So whatever info you have in x2, you also have in x1. x1 doesn't have anything more information than x2, or the other way around, if they're linearly dependent. Because I can also write this equation the other way around, right? I can say x2 equal to x1 by alpha, so alpha inverse times x1 minus b. So either way, it's a linear equation with different coefficients and intercepts. So then when you're trying to predict y using two completely linearly dependent variables, you basically have one useless variable you need to drop. So the VIF is measuring, so this concept of linear dependence amongst your input variables itself is called multicollinearity. So your VIF is an index for measuring that, if it's multicollinear or not. But if you had variables in an ideal situation, if you had two variables, you need to have some reason behind why to use two variables instead of one, right? And the reason is if these two variables are not completely linear dependent, you cannot write them down in this form, then it means there is some information in x1 that cannot be explained by x2. There's something new that x1 is bringing to the table in predicting y. And same way with x2. There's something in x2 that cannot be explained with x1 just through a linear dependence. So, yeah, if you have a data set that's with a million variables and say have a very rich data set, but if the fact is all of them are linearly dependent, if there's this multicollinearity, then maybe then all you have is one variable. You don't have a million variables from a regression context. But if they're not linear dependent, then all the million variables are bringing something new to the table. So that's what the VIF is measuring.
Okay.
Yeah.
So how does our model depends upon the VIF?
Yes. So you don't want to have a collinearity. So you want to have as low a multicollinearity as possible, because this is your equation. Your model is like this. You have beta 1 here, right? That's beta 2. If these two are collinear, I can plug in some newer alphas and betas and make it seem like y is only dependent on one variable, because I can write x2 in terms of x1 as well. And then the betas and all coalesce together and becomes only one equation. It will look like y equal to some specific beta based on that algebra times some x1 plus c. Or for some other beta plus c, you can put x2 in here. So it means you're only using one variable to predict it, which means the rest of it is basically useless. because the model will, if there is multicollinearity, it will figure out these betas automatically. So it can always be reformulated with a smaller set of variables. You'll still get the same amount of error. And also in terms of the VIF, variance inflation factor, there's a way you can measure it, which is what this is doing. So yeah, so it depends on the R squares. Now, we've not defined R square as well. So if you see the output, there is also something called R squares. So we first need to talk through that. Here, the R square. So once you figure out what R square is, then you can figure out, you can understand what 1 by 1 minus R square is, which is the formula for VIF. So yeah, so the R, we're not going to get into the detail of it because this needs some analysis variance, but R square interpretation point of view, the larger the R square, the closer to 100% you are, the better the model. The better the more model is explaining your predictions. So now you know, based on the VIF formula, you know that it is how it is related. So this is basically the inverse, and then a big number becomes a small number, right? So if say R square is 100%, it's a good thing. Now let's see what happens for VIF. 1 minus 100%, or like 1 minus 1 is going to be a very small number. So this kind of explodes to a very large number. So the larger it is, the better. So if you see 1 by 0.1 is what, 10, right? Whereas there's 1 by 0.2 is 5. So basically the smaller this number, you get the bigger the VIF, and the smaller it is, it's also good. It only is possible when your R square is close to 1, which I told you is a good thing. So basically, that's how you interpret it in terms of interpretation. So usually in practice, identifying the fact that there is linear dependence is useful. These days, packages do it for you themselves. So there's a package in R called Caret, which measures linear dependencies, for example. So find linear combos is the function in the Caret package, which automatically tells you what the linear dependencies are. And another way to measure linear dependencies is if you had a matrix of your variables, your input variables like this. So now I'm talking about how the linear dependencies are figured out, right? Okay. All I'm saying is these variables need to be independent, linearly independent of each other. So they cannot be written down in this form. Then there is no linear dependency, which is the same as saying measuring the rank of this matrix. The definition of the rank of a matrix is the number of linearly independent columns. So if this matrix had column rank of 3, it means it already has all columns being linearly independent, which is a good thing for a model. So one thing you can do is, instead of computing R squared, then computing VIF and doing this thing in your mind of R squared is big is good, so now 1 minus R squared and then 1 by and all that stuff. All you can do is just compute the rank of the matrix and see if it is full rank or not. If you had k columns and if your column rank ends up to be k, then you're in a good spot. But if your rank is much smaller, if you had 3 columns and if your rank was only 1, then it means then you know how to interpret. It means there is only 1 column that is useful. The rest of the 2 are linearly dependent amongst each other. Not just amongst each other. The rest of 2 can be explained using a linear dependency equation with the rest. So that's another way that you can quickly do. And that is the internal algorithm that basically the find linear combos is doing. So if you see this, yeah. It uses some linear algebra to determine basically if the matrix is full rank or not, and also identify the set of the columns that are involved in the dependencies. It will tell you what column is a linear combination of what other columns by what number, what the coefficients are and everything. But the question is, it first checks full rank or not. That's the internal algorithm for computing the computing what these linear dependencies are. So there are many ways around this issue. So the bigger point is, linear dependency is bad. You can measure it through the rank operation, or you can also measure it through the VIF, or you can measure it through R square and stuff. The R square, yeah, I would still prefer the rank, of course. This is a more newer, better way to do things. Because if you look at R square, you don't know which one is contributing the most and stuff, and in what proportion they're being combined with each other. You don't know the exact dependency relationship, but if you use the fine linear combination, it'll exactly tell you. You'll say X1 is dependent on X7 and X9, so either drop one of those three. Well, two of those three. If you want to use X1, then you can drop X7 and X9, basically, the other way around. Or if you want to use X7, you drop the rest. So it'll tell you what these exact relationships are. Yeah, so look at this again. Let's see if there's other things I can... Yeah, I think these things, it's better to just study hypothesis testing and analysis of variance first before we explain these things. This is the concept of confidence interval and everything. So yeah, these are nice topics. They're useful, but let's study them a bit here. Any other questions?
No, that's all.
Okay, yeah. So let's keep jumping to the generalized linear model. Okay, so just to get some perspective with respect to the history, linear regression was basically, Gauss, the scientist Gauss. He came up with linear regression. I don't remember, but he was a teenager, like something like 16 years old when he came up with the whole concept of linear regression, derived these equations in something like 1800. So it's been like over 200 years since linear regression was invented, or the method of least squares. But in more recent times, people started coming up historically with newer models that still have linear regression some sort of a foundation, so there's some sort of an extension, and those are known as the generalized linear models. This thing happened within our times, right? Within the last 50 years. These are not from Gauss' time. Basically, what are the shortcomings that this is trying to improve upon? Number one, like I said, we've looked at the mathematical way of solving the solution, but if you again come back to this assumption that epsilon is an error that is normally distributed, then you can look at it as a statistical estimation problem. You have some random function. Everything has a PDF and CDF. Now you want to figure out how you can estimate beta naught, beta 1, beta 2. So that is done using a technique called maximum likelihood, which we'll cover later on in our course. But you would have a statistical assumption-based solution. You would have just a solution based on optimizing, like we did, minimizing the sum of squares, like we did in this particular slide. But the beauty is both solutions end up getting the same answer. So if you took a normal random variable assumption on your errors and had a statistical way of solving the answer, or this method of least squares way of solving the answer, in the end, those two paths lead to the same answer, which is a good thing. But then people started thinking about other issues. What if epsilon cannot be modeled as well as a normal random variable? What if the error is supposed to be a Poisson random variable or a binomial random variable, negative binomial, whatever distribution you like? Then what would happen is your statistical route for getting the answer would be different from your optimization route of getting the answer, like we did here, least squares. So then people try to think about how to model it, not with such a strong assumption of just normality, but with other distribution assumptions as well. So that based on your data set, whatever is the best assumption to take among this choice of distributions, you take the best choice after that, instead of just sticking to Gaussian always. Maybe there's some assumption that will give you a better error in explaining the predictions. Another shortcoming or improvement people start to look at is, this is a linear equation. Everything is not linear like we saw in these plots somewhere, right? Here, a linear equation will have a lot of errors that is not explained. So maybe we want to try some sort of a nonlinear equation. So what people started doing is they take the same model, they take the distribution assumption of other distributions allowed for, and then before this function, they pass the result of this function, basically this function, into another function, which is a nonlinear function now. So let me show you the slide that I was going to show at this point. So if this was your linear combination, which you saw in linear regression, your linear regression model, if you pass that result into another function, g, which is now a nonlinear function, then the people call it a generalized linear model, but your result is going to be nonlinear. It's not fitting straight lines, it's fitting different curves. So it might explain the data a little better. And in most cases, it does. There's a very popular technique. Now, generalized linear model is a family of techniques. It's not one technique like linear regression. Based on your distributional assumption you're taking on your epsilons, you get different models. So if you put a Poisson assumption, you have a Poisson GLM or a Poisson generalized linear model. If you take another assumption there, you get another thing. There's a very, very popular classification technique called logistic regression. I know it's called logistic regression, but in the end, it is used for classification problems for a reason. There, the assumption on your epsilons is that it is binomially distributed, and your G has a very specific function. Definition. So if you use that particular G with that assumption, your generalized linear model logistic regression technique. So this is producing different kinds of techniques based on your assumptions. Now, there are some other statistical aspects of this going on. As you see, your output that you're trying to predict is, from a statistical point of view, is the expected value of y if you took the statistical route, right? Because y is a distribution, you want to take on average, what do you think y is most likely to be predicted? It should be predicted as. So the expected value of y is what it is going inside, right? Because when you do x beta plus epsilon, that's x beta that you use here, you're basically using expected value of y that you're trying to predict. So your G is a function of expected value of your response is what you're measuring. So let's keep going. So what you want to predict is that, right? The expected value of the function. So that can be written as the inverse of this function. So let me show you a few things here. So let me show you a few things. So we have some data like this, and since you're at each point of your x1, x2 of your input data, you're predicting the expected value of a distribution that you choose, whatever distribution. Say we chose Gaussian, so the Gaussian mean would lie here. So what you're essentially fitting is a different Gaussian at each point that you think is the right thing. Mean, this Gaussian has a different mean, this Gaussian has a different mean. So that's what you're predicting. And then the generalized linear model says you have x beta, which is your linear regression part, and then you're passing it into a link function. So we are passing it into G inverse. Now, this is some nonlinear function of your input variables. Now, the thing is, in the end, this is what you're doing to measure the expected value of y equal to this. So this is your regression model. It's no longer x beta. It is your expected value of y. In linear regression was just x beta plus epsilon, but here it is G inverse x beta plus epsilon. Now, there are some issues here. If you took an assumption that y was Gaussian, it's okay. But if you took an assumption that, say, y was distributed Poisson, or like epsilon is Poisson distributed, so y ends up being Poisson distributed. The thing is, the expected value of a Poisson, which is the mean of Poisson, which is denoted by the lambda parameter, has this domain of values that it's always going to be greater than 0. It's all equal to 0. So it cannot take negative values. Use whatever G inverse in here, because x beta can end up giving you some negative values for some particular entries, right? So expected value of some ith row will give you the ith row of xi times some coefficients you're measuring, right? Now, if I use whatever function here, I cannot restrict the output of this to only be greater than or equal to 0. So a good way to make sure, this is like a gatekeeper, so that you're making statistically the domain of those values that it can take get matched by whatever the range of G inverse is. So whatever G inverse is returning should match the interval that this value can take for your given assumption, for the domain of your mean of this distribution. So if you're constrained now, if you took Poisson, the constraint is it has to be non-positive. It has to be non-negative, which means it has to be positive. So one way to do that is if you define G inverse as exponential function. You know the exponential function, right? E power x. So if you define it as the exponential function, we know that the exponential function is always a positive function. It is not defined here on the negative side of the number line. Exponential is only defined here, like this, or negative exponential is like this. It's always a positive. Whatever you feed into it, even if you feed a negative number, Because if you feed an exponential of -1, it means it is equal to 1 by e power 1, which is again a positive number, because e power is always a positive. So even if you feed in numbers from negative the number line, it's only going to return something on the positive side. So that's the beauty. It's a positive function. So if I put g inverse equal to exponential, then my issue is satisfied, because I want to model it using Poisson data distribution, because that might explain it better than the Gaussian assumption. But then it's also matching that x always has to be greater than or equal to 0. So if I use exponential, whatever happens inside goes through the exponential function, it only returns a positive number. So now, here in generalized linear models, I said it's a family of models based on the distribution assumption you take. So if you take a Poisson model, which I drew here, then this is a Poisson GLM. So every distributional assumption, which is, say, Poisson, has a specific function for G inverse. This is known as the link function. It's kind of linking the domains to match. So a Poisson GLM has a link function of exponential. A binomial GLM has some other link function. What is the link function for linear regression? A linear regression is also a GLM. It's a Gaussian GLM, basically. So linear regression is just a special case of GLMs, right? Because in linear regression, you're taking a Gaussian assumption here. Your mu is the mean expected value for a Gaussian distribution, and mu does not have any situation like this. It can take any number between positive, negative, whatever. So basically, you don't need a G inverse to match these domains to match up. So G inverse is just the identity. So it's not doing anything, basically. It's equal to 1, basically. G inverse is 1. It's just not doing anything. So that gives you the special case of a Gaussian GLM, which is a linear regression, or which is also called a GLM with the Gaussian assumptions, with the identity function of identity, with the link function of identity. So every distribution, you'll have a table of what distribution GLM you're taking and what its link function is supposed to be. So for Poisson, it's exponential. So if you do something like GLM link function, you will get, I'm very sure, some table. So let's just do wiki, for example. So this is a table. Normal distributional assumption, linear regression. Your link function is identity. You don't have a G inverse. For different distributions, you have different things. Now, if you look at Poisson, your link function is exponential, if you see. Your output is predicted using exponential of x beta. For logistic regression, which is this case, your output is predicted using a link function called the logit function, which is nothing but this. So a logit of x beta is equal to e power x beta by 1 plus e power x beta. So this is another technique. So based on, now if you have a situation where you don't have 2 classes, but you have 5 classes, more than 2 classes that you want to predict in a classification situation, then you use a multinomial logistic regression, and so on and so forth. So there are so many models that just come from the GLM family based on your distribution assumption. And then there's a statistical route for estimating your betas, which we've not discussed, right? Because we only discussed the optimization, the math route of minimizing the some least squares error, which we need to take based on these assumptions. We will discuss that in the coming week, though. But this is just a model equation. I'm just showing how the model is defined. So this is, your output is defined like this. Instead of x beta, you're predicting G inverse of x beta for a very specific G inverse and a specific assumption on your epsilon. So this is that table that we saw in wiki for different distributions and stuff, and different link functions. Okay, so I think this is a good point to give it a stop. Any questions? We're going to cover a part 2 of generalized linear models. We will cover logistic regression and whatever I talked even more in detail.
Very interesting, Praneeth. I think once I go through this, the GLM, I should go in depth.
Sure.
So in some cases, a couple of things are really still not clarified, but at this moment, asking question not makes sense. To go through some kind of underlining concept.
Sure, yeah. I think that is a process. You go through it for a while, think about it yourself, and then again you come back to me, and then meanwhile you will listen to part 2 as well, so your understanding keeps improving. Yeah. So, okay.
Hi, Praneeth.
Yeah, go ahead.
Would you please provide us some material for the preparation for next class? Like some books we can read, some articles we can go through.
Yes, yeah, I think I like this idea. Yeah, we can do that beforehand. Yeah, I will do that. I will send an email.
Okay, thank you.
Hey, Pranit, today's class was like a high level class for me. I don't know, maybe it's because since long time I have been not doing this like linear regression. Maybe in my intermediate I had such classes. So is there any prerequisite which I have to do first to understand these?
So linear regression or GLM, you want to start with linear regression more carefully, or what do you feel more comfortable at? Where do you want to start doing?
Whichever has to be in order.
Yeah, so the linear regression is the first thing you want to do before you study GLM anyway, right? Linear is a special case of GLM. Interesting. So if you see, the only concepts I've used in linear regression is the model equation itself and how you're trying to predict, the fact that it's a linear equation. Then I talked about, in terms of predictors, I talked about the gradient or the derivative of the function. Because the function is convex function. If you set the derivative equal to 0, you get where the minima is. So you can read about minima of convex functions. You can search for it. I can send you a link.
Okay.
By setting gradient equal to 0, you can read a paragraph or two. You'll get some feeling. I'll send you some basic links, not like some complicated stuff.
Okay. Okay. Yep, thank you.
You'll feel comfortable.
So
yeah, look at matrix algebra as well. Matrix multiplication, matrix inverse, because your solution from the matrix approach is X transpose X inverse X transpose. Right? You can think about that. The operations a little bit.
Okay.
Pranit, send those links in your WhatsApp group. Just even I also wants to go through that.
Yeah, I plan to send for everyone. Yeah, I can do WhatsApp group or email is okay, right? Email may be easier as well. Because
email is fine. Sure. Email is fine.
Yeah. I'll send an email. I'll group email a few things. Sure. Any other questions? Okay, so I will send those links. You can do some more getting acquainted to it, and then I will send you some links to some R code for doing linear regression as well. From coding perspective, it's literally one line or two lines. Like you get your data ready, X and Y, but calling linear regression is just one function call. You pass your data X and Y into that function, it will give you all the coefficients, the output that I showed you in the screenshot. So that will be some assignment around it, but it will be easier.
So in the R or Python, they are already developed the algorithm or package or function we can use directly, right?
Yeah, it's just a function called directly. You don't have to do anything. You just pass the data into it.
Okay.
So it's good to do that, but still, although it's as simple as one or two lines of code, it's good to just do it and get acquainted. So that will be part of the assignment I'll be sending. It will be a simple code.
Okay.
Cool. Yeah, other things, questions?
Pranit, actually, I was not able to run the first assignment code in R. It says that it's the E10, that package was built under 3.4.2 version.
I see. So maybe your R version is older than you, or you might want to verify the R version itself.
In the document which you sent, we downloaded this 3.4.1. So.
I see. So
yeah.
3.4.1 seems to be the most recent R version. Let me get to the bottom of it. Let me check up. Let me see E107's version that it requires, and let me see what. Okay.
Even I got the same issue.
Sure. Yeah. If it's a version, you got a warning or you got a complete error?
Warning. It's a warning message.
So warning, it will still work. For the other guy, for Shashidhar, what do you remember? If it's an error, it was a red warning.
Let me check once.
Yeah. Or you can try one thing. You can just type library of E1071 and it will tell you it loaded or not, since you already tried installing it. The second one, the library of E1071. You can also share screen. That's another way as well. We can do it quickly.
Yeah, that's what I can share my screen if you want.
Yeah. So that, yeah.
Just let me know if you are interested.
For some reason, I don't see the screen. Raghu, do you see a screen?
No, I don't see.
Yeah, you can try. Click on share and then click on your entire screen. And then click Interesting. It's not seeing screen.
No?
Yes.
Yeah.
Yeah.
Yep.
Let's see. We did. You're talking about the E107 right? Yeah, it seems loaded from what I see on the right. It says user library. But let's check if it's functional or not. So in the console below, instead of in the code window, the below window, just type library parentheses E107. Yeah, yeah. You don't keep space. Library after the Y. Open your E1071. Yeah, I'm very sure it is loaded, but let's confirm it is functional. Any issues? Enter. Yeah, so this is the warning. You can ignore that. It is still gonna work. Yeah.
Pranit, so house votes 84 did not work for me.
Yeah, the data set.
The data did not load, huh? Oh, it says the same thing. The data set not found. I see. I think it is coming from another package. Okay, so let's do one thing. Okay. Okay, the data set is in another package. It's in a package called ML Bench. So just an example data set for people to play with. So if you install the package ML Bench, just like install 1071. So install.packages. Oh yeah, either way you can do like that as well. ML Bench. Yeah.
Okay.
Install it, then you do library of ML Bench, then it gets loaded into your session once the install is done. Install is always one time. You don't have to install every time.
Yeah.
To restart your computer. Yeah, now you do library of ML Bench. ML Bench and enter. Now try, ignore that one. Now try data of household 84 with both lines started. Yeah, now it's loaded.
Yeah.
Okay.
Yeah.
I think it should work now.
Yeah. Sure.
Okay. Thank you.
Cool. Okay, so let's catch up next week. You'll definitely get some emails after a few hours today. For next week. All right. See ya. Have a good one.
Thanks, Pranit.
Okay, thank you.
Okay, bye-bye.
Bye.